Good morning, good afternoon, good evening, everyone, ladies and gentlemen, damas y caballeros de Sudamérica, senhoras e senhores. Welcome to the fifth ALAGO webinar. My name is Alexandre Ferreira. I'm a petroleum chemist from Petrobras Research and Development Center, speaking directly from Rio de Janeiro. And I work at the Geochemistry division, more specifically at the Fluids Technologies Management for almost 20 years now. I'd like to thank the association for this invite to be the host for Dr. John Eiler's talk tonight. Our sponsors, of course, SAINS, Analytical, Thermo Fisher, and Faperge, and you for your audience today. Well, as you might know, the organizing committee of the 2020 ALAGO meeting had to cancel the event last year due to the COVID pandemic, but came up with this idea of having a sequence of webinars inspired on a similar event organized by UENF, State University of Northern Rio de Janeiro, which was a hit, it was a success. So the idea was to bring together once again the members of the organic geochemistry community, testify some of the last developments from key research groups. Well, I have some messages to pass tonight. Well, don't forget to follow ALAGO on social media. I mean, Facebook, Instagram, and the channel on YouTube. These are very powerful tools nowadays to communicate. You can also affiliate to the association. The link is located below this video. ALAGO aims to provide news in our field of knowledge and wants you all to be part of this community. The members want to hear your comments, suggestions, and demands. And finally, last two messages. Don't miss the next webinar. It will be presented by Daniel Dubois, geochemist and a good friend from Petrobras. He will be talking about reservoir geochemistry. It's really will be very interesting. Also, don't miss the next sequence of webinars in June next month. State-of-the-art analytical techniques applied to organic geochemistry. Well, let me finally introduce you to our speaker now. His presentation, as you know, is entitled Lessons from Stable Isotopes Regarding the Origin and Chemical Evolution of Geological Hydrocarbons. Dr. John Eiler is a long-term collaborator and also a friend. He's a Robert P. Sharp Professor of Geology and Geochemistry at Caltech, where he has directed laboratories for stable isotope geochemistry since 1998. John's research spans subjects ranging from petrology to meteoritics and cosmochemistry, paleoclimate research, environmental science, organic geochemistry, and geobiology. But running through these applications is a common thread, emphasizing the development of new technologies for observing isotopic distributions in nature and new geochemical tools that take advantage of those technologies. Most of his research over the last decade and a half has focused on or the study of multiply substituted isotopic molecules in nature. More recently, he has expanded this work to consider the geochemistry of site-specific isotopic variations, particularly in organic molecules. In today's ALAGO lecture, he will explore what has been learned by applying these clumped and site-specific isotopic tools to questions regarding the creation and evolution of geological hydrocarbons. So, John, very welcome, and the floor is yours.
Thank you very much, Alexander. It's really a pleasure to be able to spend the evening, my afternoon, your evening, with a good friend and with all of my other colleagues who I hope are online with us today. And I'd also like to thank the organizing committee for my invitation and the staff for organizing this session. So let me see if I can manage my computer to show you the full screen. Oh. Am I still there? I hope I am still there. There. Someone will have to Someone will have to tell me if I'm making a mistake in the way that I'm getting things set up.
It's not in presentation mode yet. Okay, now here you go.
Are we good?
Ready,
Great,
go.
I appreciate that. We're all living through the barbarities of having to do these things through computer screens, but hopefully you're still with me. You have a little patience to still be with me. So yeah, so as Alexandre suggested, I'd like to review for you a body of research that's been developing over the last 3 or 4 years, I would say, that draws upon new technologies, new measurement concepts, new tools for examining the way that the naturally occurring rare isotopes are distributed within and between organic molecules to gain new insights into natural chemistry. And the particular problem we're going to look at today is the fundamental chemistry that's responsible for the creation and the chemical evolution of geological hydrocarbons in the Earth's interior. This is a compilation of work that combines efforts from many, many colleagues. I have a list here of students, former students, current students, and postdoctoral scholars at Caltech, and a list of agencies, organizations that have supported this work, every one of which includes a number of other colleagues who've been very intimately related with the science that I'm going to show you today. So this is really the result of dozens of people, I would say, efforts over the last years. So let's begin by thinking about some of the reasons why it is that we study what we study. This is a community at the ALAGO that is familiar with petroleum geochemistry, but sometimes there are some subjects I personally feel when I'm too close to it for too long, I forget the important things that motivate it. So let's think about that for a moment. We are living in a really unusual time in human history when the extraction and the use of geological hydrocarbons, gas, oil, coal, from the Earth's crust has created an unbelievable source of energy that is available for our society. And this has driven an historic rise in productivity, human productivity, measured in, say, GDP. And this has to be directly and indirectly related to the explosion in human population over the last century. The chemistry of petroleum is really underlying a unique period in human history. This is, of course, driving up consequences. If you have an entire human civilization that multiplies in size by 10 and does so through the use of geological hydrocarbons, then the combustion products, things like CO2, are accumulating in the atmosphere. And it's very obvious at this point that we have driven a almost 50% relative rise in the concentration of CO2 over pre-industrial levels. And it's now generally recognized that this is driving global and regional climate change. So it doesn't matter really who you are, what your background is, what your interest is, your life is enmeshed with the chemistry of petroleum. I'd like to go through 2 little vignettes just to point out ways in which this chemistry intrudes on our life, even beyond things like energy production and CO2 output. So plastics, they are absolutely everywhere. They are the foundational material of modern life. These are something that come from steam cracking of oils, condensates, and gas to make ethylene, that then by catalytic industrial chemistry makes polyethylenes and turns into your cell phone case, the chair you're sitting in, the panels on your car. It is everything. And this is something that has expanded by a factor of maybe 100 over the arc of my lifetime. Another even less familiar case, but I think it's important to realize just as an example of how deeply into our lives petroleum chemistry intrudes, is food, the food that you eat. You are directly eating petroleum, you are indirectly eating petroleum through a very complicated set of industrial processes that begin with the cracking and distillation of oil, condensate, and gas to create precursors for the petrochemical industry, one of the major products of which are dietary supplements, things like the essential amino acid methionine, most of which is created petrochemically rather than through biological means, that is, when you take it as a supplement. Some small portion of this ends up in your body directly if you take, say, a vitamin pill. But overwhelmingly, the importance of it in your diet is that this methionine is fed through agriculture into livestock. And if you eat eggs or meat or milk, or really, unless you're a vegan, you are ingesting food that was created, really built molecule by molecule from petrochemical precursors. So it is everywhere, and it has ubiquitous negative consequences for us as well. The combustion products and secondary chemistry in urban settings is an obvious daily health hazard. Dispersed oil and gas from extraction mishaps, extraction-related pollution of groundwater, solid waste of plastic. It is everywhere. The direct and indirect consequences of the petroleum age are everywhere around us. So what I'd like to focus on in this lecture is a deep, a really fundamental understanding of what is the natural chemistry that causes this to happen. Like, why do these resources exist? How are they formed? And maybe this will give us some insight into the scientific underpinnings of this modern age. So let's first remind ourselves of the materials. We're discussing the solid products of burial of organic matter, kerogens, and then the gaseous and liquid products of the breakdown of those kerogens, including gases, which will be the main analytes that we look at in the isotope chemistry studies that I'll relay to you, as well as oils and bitumens, and then a sort of intermediate fraction, which we'll discuss at in some examples of condensates, compounds that remain liquid at Earth's surface conditions, but are relatively volatile. There is a common understanding of how these hydrocarbons derive from biological materials at the Earth's surface. Biomass consists of families of macromolecular materials, lignins, sugars, carbohydrates, proteins, lipids, and so forth. And through the processes of burial diagenesis, they undergo chemical transformations, polymerizations, condensations, biological breakdown to turn into human organic acids and other, I'll call it gunk, just as a catch-all phrase of macromolecular materials, dissolved organic molecules, adsorbed organic molecules, and then some fraction of this biomass is carried through this process as preserved biomarkers with relatively little chemical transformation. Where the geological hydrocarbons begin to form is in the process of catagenesis. With further burial of these humic substances, they begin condensation and polymerization reactions that cross-link them into a solid macromolecular material, kerogen, and that kerogen begins breaking down, releasing gaseous compounds, liquids, oils and bitumens, and these lipids that are preserved as biomarkers get incorporated into those and become a component of them. Further burial catagenesis leads to cracking, that is the breaking of chemical bonds within these substances we've talked about so far, to create smaller, chemically simpler mixtures of gas compounds and graphitic residues. And the end stage of this process is when you pass through the veil of catagenesis into the metamorphic regime of the mid-crust and find yourself faced with graphite and carbon dioxide, CO, and so on and so forth. So I'm just fiddling with my computer some more. So the evidence behind this paradigm for understanding of a biological and catagenetic origin of petroleum is very clear. It's irrefutable in many of its elements. So Alfred Treves, the famous early 20th century chemist, was the first person to discover indisputably biological molecules within porphyrins from oils. Here, these are large organic molecules that are very clearly products of biological synthesis. We find the macroscopic remains of biological materials in the source rocks of petroleum deposits. So the biological origin of these compounds seems indisputable. And we have laboratory models that show us the cracking chemistry that transforms those buried organic compounds into the structurally simpler hydrocarbons that are familiar to us in oils and gases. Here's an example of an increasing time at temperature of the products of pyrolysis of kerogen, first creating aliphatic hydrocarbon chain compounds that are released from kerogens, which then undergo ring closures to form aromatic compounds, which are able to effectively polymerize with each other to make larger and larger structures, things like polycyclic aromatic hydrocarbons. And then eventually these will condense to form graphitic materials, material you might call coke. This sort of chemistry we can think of as taking place in an energy landscape where the vertical axis is the energy content of the materials, that is its chemical potential energy, and the horizontal axis, moving from left to right, is the progress of chemical reactions. It is the arrow of time. And we can think of this sort of paradigm of catagenetic production of hydrocarbons as proceeding through a series of little local energy wells, each of them a little bit more stable than the last, so that you begin with biological materials, humic substances, that are very far from thermodynamic equilibrium. They are able to undergo structural transformations, turning into kerogen, bitumen, larger hydrocarbon gaseous molecules, small hydrocarbon molecules like methane, and eventually into CO2 and graphite. At every step of the way, overcoming small energy barriers, activation energy barriers, and transforming eventually into a thermodynamically stable form at the conditions of the Earth's crust. This is all very coherent. There's a lot of evidence for it, and yet there are first-order problems. One of the first-order problems that was the focus of a series of papers by Mango in the mid-90s is that when we study laboratory models of this sort of catagenetic chemistry, we find that the gases that we produce are usually much wetter, that is, richer in hydrocarbons larger than methane, than natural gases, which are shown in these black bars. There are several different possible explanations for this that are very frequently cited in individual instances. Maybe it's biological production of methane in reservoirs, perhaps the wet and dry gases, that is, the methane and the larger hydrocarbons, separate from one another during migration. But Mango's suggestion was based upon the fact that the chemistry of these driest gases resembles hydrocarbons at a sort of metastable equilibrium at the conditions of the Earth's crust. That is, he imagined that perhaps there were reversible chemical reactions that allowed natural gas to take on an equilibrated state, sort of like a metamorphic fluid, if you will. It's a very heretical idea, but it's one that was an outgrowth of an earlier concept that Tommy Gold was a strong advocate of in the 1980s, that hydrocarbon chemistry as a whole was mostly non-biological in its origin. This is an idea that has been sufficiently discredited that most people, if you're younger than me, you probably never even heard of it. But it was a big deal in the 80s, okay? It's sort of like weird haircuts and polyester shirts. Abiogenic oil was a big deal in the mid-80s. One of the reasons that Gold was an advocate of this concept came from studies of the thermodynamic stabilities of hydrocarbons at very high pressures and temperatures corresponding to the Earth's upper mantle. And it's simply true that aromatic hydrocarbons, paraffins, and so forth have some field of stability under certain oxidation states at very high pressures. And so it seems, at least in theory, imaginable that these could form non-biologically from metamorphic and mantle fluids. And here's a quotation from Tommy Gold. He says, hydrocarbons are not biology reworked by geology, but rather geology reworked by biology. And what he means is most of the constituents of oil and gas come from mantle chemical processes without biology, and then they sort of obtain a little seasoning, if you will, of biomolecules near the Earth's surface. And so his concept was, certainly we have life at the surface and it creates biological compounds, and they undergo diagenetic transformations into things like peat and lignin and so forth. But then at the other end of the crust, within the mantle, we have non-biological chemistry that is transforming graphite, carbon dioxide, and so forth through abiogenesis into methane, higher order hydrocarbons, or organic acids. These then, in his view, were undergoing polymerizations to create oil compounds and wet gas constituents, which then act as a solvent to effectively dissolve or scavenge biomarkers within them, explaining why porphyrins and other things like them are present, and then to condense to make solid hydrocarbons, that the kerogens themselves, even in some instances at least, could be non-biological in most of their origin. So this is an idea that's been largely debunked, and I would say more forgotten than debunked. Most people can't even remember that this is what folks thought 30 or 40 years ago. But there's been a revival of this concept. And the revival mostly comes from high-pressure experimentation associated with people studying the subduction processes and the volatile element chemistry of subduction. And they have sort of rediscovered, if you will, the notion that methane has an extended stability in geological fluids, where it can be tens of % of those fluids under mantle pressures, and that under cold conditions like a subduction zone and such high pressures, organic acids might form stably as well. So you shouldn't imagine that this has a way of relating to petroleum systems that's in any way easy, because the crust, these experiments show consistently that you take all of these hydrocarbons that could be stable in the mantle, move them up to lower pressures into the crustal systems, and they will spontaneously break apart and form CO2 and water. So you can think of the crust as being like a no-go zone for these sorts of mantle hydrocarbons if they do exist. And yet, we find geological evidence that there are stable or maybe metastable, quasi-stable sources of methane, at least, in hydrothermal fields that reappear at temperatures maybe around 300 degrees centigrade. That is, most of the crust is very hostile to the existence of hydrocarbons, but when you get quite close to the Earth's surface at moderate pressures and temperatures below 300 centigrades, maybe methane has a stability field in that region. So this suggests a more nuanced, still I would say heretical, not very many petroleum geoscientists think this way, but a more nuanced understanding of something related to Tommy Gould's ideas. That the core concept of catagenesis seems sort of obviously true, and yet it may be that there are quasi-equilibrium chemistries, metamorphic-like chemistries, that start to take over at the upper temperature range of catagenesis as we get into temperatures of, say, 200 degrees centigrade or so. So if this were the case, then the energy landscape would be sort of different from the way that we discussed it before. It would be more like a pot cooking on a stove as opposed to a collapse or irreversible breakdown of molecules. In this worldview, shown here, the vertical axis is again the energy of the system, and the horizontal axes you can think of as being different directions of chemical transformation in the reaction coordinates. In this concept, you could imagine that biological materials, humic substances, are very high energy states, very unstable and prone to reaction. CO2 and graphite, a very stable low energy state, very difficult to get to back react. But all the compounds that are of interest to petroleum geochemistry are sort of intermediate states. They are local energy minima, and once you form them, they're able to interconvert somehow through metastable reactions. And so this concept of metastability, a system that can exist at a local energy minimum and therefore persist over geological times, and yet participate in chemical transformations with other materials. For example, gas components might interconvert with one another somehow. So let's now turn our attention to the isotopes. How will we use the isotopes to study this system? So let's first of all set some, let me go back half a step and set some stakes, okay? What's at stake here between these two views of petroleum geochemistry, cracking or cooking? First of all, if it's really a traditional view of catagenesis, then petroleum chemistry is basically destructive All it does is break things down. If this metastable cooking concept is correct, it is also regenerative, that complicated molecules maybe can form spontaneously from simple ones. If cracking, then the products recorded in substrates are record pathways, okay? They record irreversible pathways of history. In cooking, the chemical constituents can record conditions of recent equilibration. That is, you don't necessarily know how they got to be the way they are. They are reflecting the conditions of their reaction equilibrium. And finally, if in cracking chemistry, even the simplest of compounds like thermogenic methane should be thought of as an indirect biosignature. If cooking, well, there are a lot of ways that you could create those molecules that do not have to involve biological materials. And when we turn to the hydrocarbon chemistry of, say, other planets or ancient times in Earth history, or hostile environments in the modern Earth, this becomes a very important point in the search for organic chemical evidence of life. So now let's think about how the isotopes relate to this. So in simple overview, as I transform from large molecules to small molecules through cracking chemistry, the rates of those reactions can be dependent upon the abundance of heavy rare isotopes within the molecular structures, for reasons we'll get into in a moment. In this case, I would expect to see a selection for and against the rare isotope species as I move my way down the reaction path from large to small molecules. In the cooking concept, instead, the heavy isotopes are competing with one another energetically to occupy favored sites and favored molecules, following the rules of equilibrium thermodynamics. So let's think about some of these principles that we'll use to develop tools to answer these questions about the origin of petroleum. First of all, intermolecular isotopic separations, that is, differences in rare isotope content between coexisting molecules. We can think of the chemical bonds within individual molecules as being energy wells across which the individual atoms vibrate, okay? And these energy wells have discretized energy states that the bond can occupy because they're a quantum mechanical oscillator. And if I have a heavy isotope substitution in one of these atomic sites, the vibrational energy level I have access to is lower in energy state than if I have the lighter isotope. That means that this chemical bond within, say, ethane, if I have a C13, is more thermodynamically stable. It persists more easily, it's harder to break down. The same substitution in some other molecule, say methane, might also lead to a lower energy state, but with a more subtle effect. And in a system like this, if I introduce a rare isotope like C13, it needs to make a choice. Would I rather go into, say, ethane, where I have a big effect on the energy of the system, or into methane, where I have a small effect on the energy of the system? And in systems that reach thermodynamic equilibrium, there's a kind of sorting of the rare isotopes so that they become concentrated in the places where they do the most energetic good. And therefore, I will see a concentration of C13 in ethane relative to methane. An exchange reaction of the type I show here on the right will be driven to the right. Finally, there's an effect of temperature that tends to drive systems towards a random state, random sharing of rare isotopes between molecules as temperature gets higher and higher. And therefore, these vibrational energy effects become attenuated. They get weaker as you go up in temperature. And that temperature dependence is a characteristic trait of the equilibrium state. Next, we can note that there are intramolecular isotope effects that are exactly the same, where there is a preference to put a rare isotope into some molecular sites, like say the CH2 site in the center of propane, as opposed to other molecular sites, like say the methyl site at the end of propane. If I put a heavy isotope in the central site, it lowers the energy of the molecule a lot. If I put it in the terminal site, it lowers it only a little. And so there will be a competition where the heavy isotopes will be concentrated at equilibrium into the central site, and that equilibrium effect will diminish as I go to higher and higher temperatures. Finally, there is an effect we call clumping, a tendency of two rare heavy isotopes to stick to each other in the same molecule. And the concept here is that, say, both C13 and deuterium reduce the vibrational energy state of the methane molecule, but when they're joined to each other into a doubly substituted molecule, a clump, then I lower the energy by more than the sum of these smaller effects. That is, the best way that the molecule can organize its rare isotopes is to stick them to each other. And this, again, is an effect that will be strong at low temperature. Shown here, the vertical axis is the excess relative to a random distribution of these doubly substituted clumps. Then as temperature rises, entropy begins to take over, random becomes favored, and we diminish that excess and approach a random distribution of the rare isotopes between the singly and doubly substituted forms. These are the signatures of equilibrium isotope effects that we will hunt for in our studies of natural gas compounds. We'll then contrast that with so-called kinetic isotope effects. Kinetic isotope effects are effects of isotope substitution, not on the stability of molecules, but on their rates of reaction. So if I imagine I have, say, a long hydrocarbon like N-octane, and I'm going to crack it in half, I'm going to break it irreversibly into two smaller pieces, then this N-octane sat in a stable energy well that it has to escape. It has to overcome some activation energy, breaking in half, before it can create these fragment products. And in order to do that, it has to escape the vibrational energy well that it's in the reactant state. And just as we saw for the equilibrium effects, the heavy isotope substitution in that reactant lowers its vibrational energy and stabilizes it, makes it harder to break. There are some other nuances to this, but to first order, the heavy isotope forms react more slowly than the light isotope forms. And so if I were to look at the, say, C13 content or deuterium content of the products of this sort of cracking chemistry, then the substitutions that are immediately adjacent to the broken bond will be suppressed, because the probability that the reaction occurred is reduced in a given window of time if the rare isotope was there. The rates are lower for the species that had a rare isotope there, faster for the species that had only the light common isotope there. So this also leads to signatures of isotopic distribution that we can discriminate from the equilibrium effects. So to summarize what we just went through, imagine that we have a system of three molecules that we might find abundantly in natural gas: methane, ethane, and propane, and we would like to use the isotopes to ask, what is their relationship to each other? In the catagenetic paradigm, where the way I make small molecules is by breaking big molecules, then I would expect that the breaking of a carbon-carbon bond in a bigger molecule like propane will be associated with a kinetic isotope effect. And then I may also have secondary chemistries that come into play, like I may acquire a hydrogen atom to cap this, the carbon next to the bond breaking event and create a stable ethane molecule or methane molecule. And that these processes will have distinctive isotopic signatures on their products. If instead the cooking concept is right, and that we are experiencing systems that have reversible chemistry, more like a metamorphic fluid, then it's the equilibrium thermodynamics of separation of rare isotopes between coexisting molecules, distribution of rare isotopes between adjacent sites, and the probabilities of clumping within each molecule. They will follow the rules of equilibrium thermodynamics. So let's look at four test cases where we apply these concepts to get an insight into the way that petroleum generation works. We'll look first at lignites, things that are very early in the process of formation of kerogen and part of the solid residue. Then we will look at the formation of hydrocarbons during oil formation processes early in the petroleum generation process, then later in the petroleum generation process. And then we'll look finally at some of the larger, more structurally complex molecules that can persist through the gas generation. So the ways that we're doing this involve technologies that if you could put me in a time machine and let me go back and show some of the data that we're able to generate today to me as a graduate student 30 years ago or whatever, I would have thought it was magic. There's a lot of magic that's happening in high-end stable isotope geochemistry right now, and it's the confluence of a variety of technologies. High-resolution sector mass spectrometries using different platforms, Orbitrap or Fourier transform mass spectrometries, absorption spectroscopy, NMR spectroscopy. This isn't a technology talk. We're not going to go into the details, but I encourage you to read up on what is happening in the technological front to generate this sort of data that I'm going to show you. A key concept, just to let you understand what kinds of measurements are being made to observe site distributions of isotopes and clumped isotope distributions of isotopes. Most of the data that I work with comes from mass spectrometry, high-resolution mass spectrometry. And the concept here is that you'll take a molecule and ionize it in such a way that it breaks up into fragments, each of which comes from a different part of the molecule. And then if we look at each one of these fragments, it will exist in its unsubstituted form, in its singly substituted forms, in its doubly substituted forms, triply substituted forms, and so forth. And if we look at each one of these cardinal masses with a very high mass resolution instrument, we will see separations between them. Say the double 13C substitution and the 13CD substitutions, they will be separated from each other even though they share a cardinal mass. So if we're able to do this for both a full molecule and its pieces, we can observe both the clumped isotope compositions of these molecules and get constraints on the distribution of rare isotopes within their structures. So let's now look at the case of lignin. So lignin contains methoxy groups, methyl groups, CH3 groups attached to oxygen that hang off aromatic rings that make up most of the backbone of the structure. And as you undergo catagenesis, these methoxy groups are removed from the structure, both by biological processes early in diagenesis and then by thermally activated processes during catagenesis. So what was done, this is work by Max Lloyd, was to take lignins and expose them to iodic acid, which cleaves the methyl group from its oxygen and makes methyl iodine, which is then reacted with a fluoride to make methyl fluoride. And that methyl fluoride can then be studied by high-resolution mass spectrometry to determine its C13 content, its deuterium content, its clumping, and so on and so forth. So this gives you an example of one of the ways that we get data of this type. When this is done, what we find is that the carbon-13 content of the methoxy group gets driven up enormously by 60 per mil. This is basically the amplitude of most of the carbon isotope variations that you see in bulk materials on the Earth, except here it's happening at the scale of an individual atomic site within lignin. The lignin itself as a bulk material is basically unchanged in its carbon-13 content, but this one site, because it's so reactive, is showing you that it is the residue of an extensive degree of chemical reaction. And so as we work our way up thermal maturity, time at temperature, manifested by the vitrinite reflective index, we see this distillation up of the carbon-13 content. And it's an effect that's so strong, it clearly greatly exceeds the equilibrium effects that we might expect to see by reversible redistribution. So here's an example where the classical catagenesis paradigm for thermal evolution of buried organic matter is perfectly correct. This is an irreversible cracking chemistry. Now let's go look at methane, which is one of the first products of catagenesis and then continues to be a product throughout the entire process. So it's a wonderful thing to track all the way through the catagenetic process. So here we're going to look at two different versions of the double substitution. One of them where we have a carbon-13 and a deuterium, and that's the 13CD axis, the horizontal axis here. And the other is the double deuteration, the D2 excess in methane. For equilibrium processes, there is a correlation between these two measurements so that at low temperature, both of them are big, at high temperature, both of them are small, and at equilibrium, they have to follow a coherent correlation with each other. When we go and look at methane that is created by irreversible catagenetic processes in the laboratory, it deviates very strongly from that equilibrium relationship. Here we're seeing the previous plot, but at a bigger scale, where you can see that the products of cracking long-chain hydrocarbons in the laboratory have deficits in this doubly deuterated form that are on the order of 50 per mil. This is a big deal. This is a big effect. And our explanation for it is that 3 of the hydrogens in a methane produced by cracking are inherited from the methyl group in the reactant, but the 4th one is a capping hydrogen, and it comes from abstraction from some other substrate. It could be a hydrocarbon substrate or it could be water, but however it's made, it's very low in deuterium content. And when it mixes with these other 3 hydrogens, it creates what's called a combinatorial isotope effect that expresses as a big deficit in the probability of double substitution. When we now go out of the laboratory and into geological environments, we see that this deficit in the double substitution is present at low thermal maturities, either low RO values of source rocks for unconventional gases or low delta 13C gases in conventional reservoirs. That signature is clearly there, but then it's erased as you go to higher thermal maturity. Basically, you approach the equilibrium state as you get into the upper oil window, lower gas window conditions. Now let's switch to another tool where we're examining the distribution of deuterium between the center of the propane molecule and its end. Cutting out all the middleman of the experiments and the rationales, which we've already discussed, the finding is very similar to the case of methane. The equilibrium fractionation of about 50 per mil is shown as this gray band. Here we're showing the equilibrium relationship as a blue curve. When we see low thermal maturity natural gases, they have big departures, either negative departures or positive departures, depending upon the substrate that was being cracked. But then as thermal maturity rises, either thermal maturity in a source rock or storage temperature in a reservoir, time at temperature erases this signature and drives you to the equilibrium state. Interestingly, this happens at the same time for propane and for methane. Propanes and methanes both begin their lives far from equilibrium in their isotopic structures, and then they reach equilibrium in their isotopic structures together. Now let's look at the intermolecular fractionations, the differences in deuterium content between coexisting molecules. Here you have to use your imagination a little bit, or your geometrical visual reasoning. Imagine that there is a composition space where we have the deuterium content of all 3 of the abundant hydrocarbons, methane, ethane, and propane, defining a coordinate system. And there is a surface that is the equilibrium distribution in that coordinate system. And what we're plotting here on the horizontal axis here, or the vertical axis in the lower figure, is the distance from that equilibrium relationship. What we observe is that there's a strong propensity, just surveying all natural gases that have ever been studied, to cluster close to this equilibrium distribution, and that departures from that equilibrium distribution are exclusively seen in low thermal maturity gases. And they reach equilibrium at the same time we see the methane and propane internal structures equilibrating. The suggestion from all of this is that there is a common reaction scheme. There is a chemistry that kicks in around the start of the gas window in petroleum systems that allows for the mutual equilibration of the gas constituents with each other. And we refer to this as a metathetic equilibrium network. That is it's a phrase that refers to a reaction network where no one reaction is reversible. That is, if I take butane and crack it, I don't immediately take the products of that cracking and recombine them. But further reactions of those products can loop their way around and recreate the original reactant several steps down the road. These sorts of reaction networks are known to exist in theory and in laboratory models, and we are suggesting that their common existence in hydrocarbon systems is what allows them to equilibrate. Let's jump ahead a little bit. There are exceptions to this system. We know when we look at larger aromatic structures, like the ethyl toluenes, we see departures from these sorts of equilibria. I'm going to have to rush, I'm afraid, because we're getting close to the top of the hour and I'd like there to be time for questions. But let me simply point out that if there is some equilibrium relationship among the carbon isotope versions of the ortho, para, and meta isomers of the ethyl toluenes, that one of the isomers has been seen to violate that relationship. And when we study its isotopic structure in the lab, we find that the meta isomer has a very strong C13 enrichment in its terminal methyl group. That really it's just that one atomic site that is responsible for this non-equilibrium effect. And we infer that this is because some of the isomers can interconvert with each other, but then the meta isomer undergoes an irreversible destruction, telling us that the gas chemistry, the reversible gas chemistry we see, it has limits. There are only certain compounds that can participate in it, and others get outside of it and go back into a cracking chemistry. So let's wrap up by summarizing what it is that we've learned about the chemistry of hydrocarbons and the validity of these two different views of petroleum geochemistry, kinetic control versus thermodynamic control. We've seen that the onset of gas generation follows a classical irreversible catagenetic chemistry. And yet, when those systems are allowed to thermally mature to temperatures above, say, 100 degrees centigrade, they reach a metastable thermodynamic equilibrium. They're able to initiate and sustain reversible families of reactions. When we follow more complicated species like the ethyl toluenes and the condensate fraction, they remain in a cracking sort of chemistry state. Their structures are a little too complicated to recreate through the radical reaction networks. But storage of the C2 through 5 N-alkanes, which are relatively stable above temperatures of 100 degrees, they can stay in this metastable equilibrium state, even in some reservoir conditions. Due to time limitations, I wasn't able to show you the impact of biological processes in reservoirs, but there's a similar sort of theme. We see that biodegradation of larger compounds follows very clearly kinetic mechanisms, whereas the cycling, redox cycling of methane and CO2 drives both the methane itself and the methane CO2 system into equilibrium, even at low temperatures. So to sum up, we've shown that at the onset of gas, oil, and bitumen formation, really the chemistry depends on source substrates and history, the path of thermal evolution. But as these systems get to higher thermal maturities, they reach a metastable equilibrium state that depends on their conditions, their temperature, their pressure, their oxygen fugacity, and so forth. I still want to point out Tommy Gold was still wrong. Okay, petroleum systems are not rooted in mantle abiogenic chemistry. They're obviously rooted in the burial of organic matter, but there is an important point here regardless, that once they reach high thermal maturities, they begin to be telling you more about the conditions they have been in and less about the paths that they followed to get there. And I will stop there so we have a few minutes to take questions.
Thanks, John, for your excellent and dense talk.
Yeah.
I'm sure it's not an easy topic to. There's too much to think about. I'm sure people didn't follow 100% because it's really a very tough topic, but very interesting. It's very exciting. Very. We are working together on this, so I'm suspicious to talk about it, but.
Oh, you can talk about it.
Yeah, but it's really very interesting. So let's see if we have questions from the audience. I can see Tamara here saying, Tamara from Federal University of Rio, thanks for the presentation.
Yeah,
I'll know more about high resolution.
So thank you very much for your questions, Tamara.
The application possibilities.
Yeah, thank you very much for your questions, Tamara. So there are basically two different ways that high-resolution mass spectrometry is opening up the subject. There's a way I would say is rooted in classical technologies, mass spectrometers that resemble things you would see in a normal isotope chemistry laboratory, where you're doing a magnetic sector separation of the ions and just doing it better than we used to do. This is sufficient for us to study the isotopic forms of small molecules like methane and ethane and propane. The bigger molecules, the toluenes and bigger PAHs, long-chain hydrocarbons, all of these are being studied by really a new type of isotope ratio mass spectrometry. It's an adaptation of Fourier transform mass spectrometry, which I encourage you to go look up in Wikipedia, where there is no big magnet, okay? You are causing the ions to orbit each other in a little teeny cavity and listening to them with an antenna. And if you can, I know it sounds incredible, but if you listen to them carefully enough, you will hear their differences in, that is, in an electromagnetic way, you will hear their differences in rotational frequencies. And the mass resolutions of this kind of mass spectrometry reaches up into the millions and allows us to pull apart all the fine details of the mass spectrum of big molecules. This is being used for hydrocarbon geochemistry, the way I described to you, but also for many other things, for the biochemistry of amino acids, the origin of life chemistry of amino acids and other compounds from meteorites. It's a big thing. It's quite new.
Thanks, John. I can see other questions.
Okay. Yeah, I see Eugenio. Yeah, so maximum burial depth. This is a great question. Of course, it's one of the big questions that you have when you are studying basins systems, whether you want to find oil and gas or you just want to study their geology. So I would say yes, with a caveat. Okay, if you find systems that have equilibrated, meaning if you can prove that a gas has reached the equilibrium state, then the state that you see tells you the temperature at which it equilibrated. And so because it gets easier to equilibrate, the deeper you get, the hotter you get, the most likely state you will find that has equilibrated is the deepest state, assuming it can escape. So if you drill into it, that will tell you what's the hottest that gas ever got. Or if it fills a reservoir that is cold and it can't re-equilibrate in the reservoir. But there's intervening processes, okay? If you fill a hot reservoir, now it can re-equilibrate in the hot reservoir, and it may erase knowledge of its earlier history.
Okay, there's Marcelo now from Fluminense Federal University.
Yeah. So is there a clock? Yes, this is at the absolute cutting edge of both clumped isotope geochemistry and carbonates, which is a more mature part of the discipline, and this clumped isotope geochemistry and positional geochemistry in organic molecules. In both areas, we are realizing that because we have systems that get out of equilibrium and then reach their way towards equilibrium, this has rate constants that control it. And if we know enough about these rate constants, we can order things in time and maybe even measure residence times. So there are unpublished or very recently published works where we're basically trying to decide what was the residence time in a reservoir, or what was the residence time of a source rock at its peak temperature.
Okay, John, there's Celso now from Saints Thermal. Great talk. Which new developments in mass spectrometry you would like to see developed?
Okay, perfect. So I would say the two things that this field desperately needs involve capitalizing on the highest level of sector mass spectrometry that we have reached, which I would say is like the thermal ultra, which is in my lab, and these very novel methods of Orbitrap-based Fourier transform mass spectrometry. One thing that we need is a merging of these two things, so that we can use the ability of the sector instruments to make very fine selections of narrow parts of mass spectra, little windows of mass spectra, and then place those ions into an analytical environment where they can be studied and measured in an Orbitrap. The second thing we need is the adaptation of Orbitrap-based mass spectrometers to the isotope ratio setting, where you want brighter ion beams, you want more stable delivery, you want something that is more like a gas source IRMS, better source, maybe multiple Orbitraps that can talk to, can operate independent of each other, to basically push that technology forward beyond where it has been built for the simple identification of molecules and turn it into more of a quantitative platform for measuring very precisely amounts of molecules?
Yeah, the clock question I saw now from Darius. Darius is still is in France drinking a glass of wine, according to him.
I'm jealous. I'm so jealous.
I talked to him earlier. Yeah.
Yay.
So that's Miguel Fernando from UND, North Dakota. So
Yeah.
Hi. Is there an implication of the concept of cooking and not cracking to try to reverse some processes of biodegradation of crude oils in the laboratory?
This is an interesting idea. So yeah, so the radical, so there's two basic ways that the cooking chemistry could be supported. One of them I mentioned because I kind of like it better. I favor it, I would say, as a hypothesis. That's the radical reaction network. So radical reaction networks are well understood from synthetic chemistry, and you could promote them in the laboratory. There are even catalysts related to the ones that are used to make polyethylene and so forth that you could use to promote this sort of chemistry. The second possibility that I didn't really mention, but it still could be true, is that these are surface catalysis reactions, and that it's the exposure of petroleum to, say, clay surfaces that allows this to occur. I would be a little surprised if this was the whole story, because it seems to be a very universal thing, and it seems to happen in dry gases, so I would be surprised. But it's possible. And I think both of those, if you wanted to engineer this, both of them could be explored. Promoting radical production and cycling, or finding surface catalysts that will promote this chemistry.
Why do you think the C2, the ethane clumped isotope measurements, what do you think still has to be developed? Because there's the paper from Clog, there's this suspicions about the inheritance of kerogen, but then nobody explored this further.
Yeah, there are several parts of this that need like a PhD scale study, where you do it seriously. You don't do it, oh, I'll do a cute paper, I'll study 5 rocks. No. You go in, re-engineer the measurements to work with the very best instruments. 5 years ago, 6 years ago, the machines were not so good. This is really a new thing that you can do this well. Re-engineer the measurements so that you are studying ethane, you are studying propane, not with one clumped isotope species, but with multiple. Study the 213Cs together. Study 2 deuteriums together. Study 2 on the same side, 2 on opposite sides. 13C and D apart, 13C and D together. All of these can be measured. You could do a measurement that had 3, 4, 5 independent properties of the molecule and would give you basically like a barcode that you could read of the chemical processes it has been through. This now is technically possible, but the first time you do anything, it takes you a few years to do it right. So I think this is the next stage, is people will take this concept. We have sort of a concept. We have a toolkit. Now people need to roll up their sleeves and work to build it out, build out the toolkit.
Okay. Maybe just one more from me.
Yeah, of course. You are the jefe, so you get to choose.
Yeah, I have to take advantage of this position.
Yeah.
So just to let people know about the studies regarding the clumping measurements between C13 and sulfur 34. What do you have to say about this? About H2S origin, for example?
So one of the exciting things about the Orbitrap-based technologies is that they scale up to large molecules and to chemically complex molecules pretty easily, that you don't have to have a room temperature gas, you don't have to have the molecule have a low mass like you do with the Spectre machines. Because of this ability of the Orbitrap-based machines, we can start to apply these concepts to sulfur chemistry. And all the things we talk about methane and ethane and propane, why do we discuss them? They're abundant, yes, but also they're easy to study. We have studied them for many years. The sulfur gases, they have tremendously complex chemistry, tremendously impactful chemistry. Now we can study them in exactly these same ways, but no one has done it. And so the toolkit is sitting there, and the instrument is sitting on the table. A musician must pick it up and play. So it's time for people to aim these tools at that. And in particular, I think you could get a good sense of whether the sulfur chemistry of sulfur-rich hydrocarbon systems, is this something that's sort of path-dependent? They had a special precursor, it underwent a special series of reactions, or is it more like our cooking chemistry, where it's inevitable? Once these systems reach a certain thermodynamic state, a certain temperature, a certain oxidation state, it is inevitable. They must have these compounds there. So this you could answer.
Okay, there's one question from Joelma from Petrobras.
Yeah.
Thank you so much for your nice talk. It's possible to differentiate thermogenic methane from methane generated from other processes if they are a result of a mixture in the reservoir.
Yeah, thank you for your question, Jolma. So this is one of the core applications of methane pumped isotope geochemistry, is to try and both separate the origins of methane, biogenic versus thermogenic, high maturity versus low maturity, and then once you've identified the end members, to characterize mixing processes between those end members. So early, very early in this field, people thought that the natural methanes were all close to equilibrated. Then we discovered that the biogenic methanes were often strongly non-equilibrated, that when they were made by microbes, they would be very far from the equilibrium clumping. And that seemed like the answer to the question. The data I showed you in my talk showed the cracking chemistry also drives you very far from equilibrium for methane. So there's something to be figured out there. For sure, the biogenic methanes are different from the thermally mature thermogenic methanes. And so in some systems, like a high maturity thermogenic gas with a biogenic overprint, this will be clear. In a low maturity system, say you go to, it's RO 0.8, you're in the Gulf of Mexico, everything's barely starting to cook. Now you have some trouble because the biological chemistry is irreversible, the non-biological chemistry is irreversible. They're doing some similar things. Now you need more tools, I think.
All right, I think it was the last question. John, again, it was a big pleasure to receive you here tonight.
No, the pleasure is mine. It's wonderful.
I just need to remind people about the next talk from Daniel Dubois. He'll talk about reservoir geochemistry. Please don't miss the links in the page. So there's link for the ALAGO social media, links for the YouTube channel, or the links to subscribe for the next talks, so you can find everything there. Thanks for the audience again, for the sponsors, and have you all a good night. For you too, John. Thank you very much again.
Bye-bye. Thanks, everybody.
Bye-bye.
Okay, thanks everybody.